Thanks very much. My goal this week has been to sort of show you how I view this whole thing, and trying to understand the cometric property and focusing on cometric association schemes that aren't metric, and to try to understand these Q-polynomial schemes. There are these beautiful examples that I tried to start the week with. Then, in order to prove any of the basic theory, it turned out that we needed these tensors that showed up in earlier work of Deinmeier and Terwilliger, Suzuki, Dickey, and so we're finishing the week talking about those tensors called scaffolds. So before I do that, I want to tell you about these circular planar graphs. So a graph is circular planar with a root set R. If you can word the graph inside a circle in the plane, the root nodes are on the boundary. So Yves Colomb de Verdier introduced circular planar graphs, and you'll see a connection between what I'm doing and these circular planar graphs almost immediately, right? So if you have a circular planar graph, let's say a circular planar digraph, you can compute its dual, and the dual is a little bit different from the planar dual. So now I take, for each region inside the circle, inside the disk, we put in a node. All of the arcs are now rotated 90 degrees counterclockwise to join adjacent regions. The regions that are touching the boundary are called root nodes of the dual. And you notice that if I have 5 root nodes, then the dual also has 5 root nodes, because the 5 root nodes partition the circle into 5 arcs. And so the number of root nodes is preserved in the circular planar duality. Okay, so that's a circular planar dual of a circular planar graph. Let's go back to these ones here. What's the circular planar dual of this graph? Same thing, right? Just drawn differently. Circular planar dual of this one, same thing, right? Circular planar dual of the triangle is the star. Circular planar dual of the star is the triangle. Let's see what the circular planar dual does to scaffolds. Let's take a second order scaffold with this series parallel reduction. So I've chosen the series parallel graph intentionally. So this is A entrywise B, and then that's multiplied, matrix multiplication with C, times matrix multiplied with E, and then we take the entrywise product of the two. We take the circular planar dual, and the matrix multiplication and entrywise multiplication are swapped. Right? So the dual diagram, creating the dual diagram is exactly swapping entrywise multiplication and matrix multiplication. Oh, I realized I can take my mask off. I'll be less muffled. Okay. So the circular planar dual corresponds exactly to swapping entrywise multiplication and matrix multiplication. And there's this strange thing, association scheme duality. Association scheme duality is somehow connected to linear programming duality. It's somehow connected to duality of character theory. There are all these duals in mathematics, and it's really strange when they sort of coincide, even partially. Okay, so I'm going to get back to this. Okay, so we're going to assume that our edge weights are inside a coherent algebra. So the set of all matrices with rows and columns indexed by this finite set X, mat XC, is a coherent algebra. So it's a vector space of matrices, rows and columns indexed by X, that's closed under the transpose operation. So automatically closed under the conjugate transpose operation. Those are the same statement. It's closed under matrix multiplication, closed under entrywise multiplication, and contains the identities for those two multiplications. Okay, so here's the coherent algebra. Coherent algebra is commutative if only if it's a Bose-Mesner algebra. So adjacency algebras and association schemes are the commutative coherent algebras. Closure under matrix multiplication and entrywise multiplication, you can see from the previous slide, this is exactly the kind of thing that we need in order to make sure that the series parallel reduction can be done on diagrams and stay inside the set of edge weights coming from that set A. I think I've made errors, many errors this week, but in particular, I have not done a perfect job of calling the elements of X vertices. Imagine X to be this large set. I'm thinking of the vertices of the association scheme. In the diagram, those things in V of G, I want to call nodes. Okay, nodes and vertices. I'm trying to use that language differently. So on a small number of nodes, we talked about these scaffolds. So the definition allows us to say that a red dot with a loop is the diagonal. That's a first order tensor, so that's just a vector. in our ordinary linear algebra sense, and that's the diagonal of the matrix M. If I forget the details about which entry came from where, and I just sum them up, I get the trace. Identifying the vector space with its dual space, we can think of each matrix as second order tensor as a scaffold with two red dots. The sum of the entries comes from hollowing out those dots. Particularly, I haven't mentioned this, but whenever you have an identity of two scaffolds with, let's say, 17 red nodes, if I take corresponding red nodes in the two sides and make them hollow, those identities are still valid. Okay, so when you try to build identities, the more red nodes you can get into your identity, the better, because then every time you sort of trace away one component, those identities are preserved. Ordinary matrix multiplication is series reduction, parallel entry-wise multiplication is parallel reduction, and the fundamental vanishing prime parameters and intersection numbers correspond to vanishing third-order tensors. Okay, so it all fits together surprisingly nicely.
Okay, sorry. So I think this is related to what you're just saying, but it isn't quite follow. So, like, if I remember correctly, this is what kind of threw me off yesterday, is that there were like parallel things that were hollow at the end, and then you said it was component-wise multiplication or something, or
yes.
So like it not matter there, but then it does matter if you have like a loop or just a single edge, like whether or not they're hollow, the endpoints are hollow or not.
So here, this vertex has to have degree 2, otherwise the sum involves other terms. So this is matrix multiplication. But in general, if I can prove that these two are equal as second order tensors, then if I hollow out one side of either, or if I attach on more of a scaffold to either side, this local move is still valid, because it's valid as long as every single node that touches the outside is red. Okay, so when I embed these things inside larger diagrams, this is coming up in a couple slides from now. If I embed these in larger diagrams, any identity that's true is still true as long as inside the larger diagram, the only nodes that interact with the rest of the diagram were red inside within this identity. Okay, so I can attach a diagram. I can apply this operation in a diagram as long as this node doesn't touch anything else. But these nodes can interact with anything else, and this identity of tensors can be applied inside a larger diagram. Does that answer your question?
I felt like there was something that was like parallel reduction, where like those nodes were both hollow.
So now there is an identity EJ, EK. So this is sort of a fundamental thing. They usually have hollow like this. And you have three primitive idempotents, EI, EJ, EK, that this is a scalar. I think it's cardinality of X times QIJK times MK, something like that. I forget exactly what the scalar is, but something like this. And this scalar is 0 if and only if the prime parameter is 0. Let's go back to the definitions. We have a finite non-empty set X in MatXC. The edge weights are going to come from matrices with rows and columns indexed by X. Our diagram as a directed graph, small number of nodes. This is not related to the association scheme that we're studying. Small number of nodes, V of G, and directed edges, E of G. We have an ordered subset, or if every once in a while we're stuck with an ordered multiset, but I really don't want to deal with that, of root nodes. Those are going to be the components of our tensors. And we have a map from edges to matrices. So the edge weight is a matrix. Every edge weight is a matrix. And the scaffold is just basically the sum over all possible images of vertex 1, sum over all possible images of vertex 2, and so on. So we just think of those as all functions from the vertex set to X. Right? This is just a concentric sum. If there were 10 nodes in the diagram, then this is just a 10-fold sum. So this is just a way to write down those concentric, those nested sums. And then for each of those sums, we take the product of the edge weights, and we take the row and column indexed by where those vertices ended up. But we only record the information according to where the root nodes ended up. Okay? Other nodes, we're just summing over those things and forgetting where those contributions came from. Okay? So this is the standard basis vector indexed by the image of root node 1 under onto that function phi. So this is our definition of the scaffold. There's something a little more general that you need. Emily's asking questions about how the root and hollow interact. In order to prove that those local moves are valid, you have to sort of make a slightly more general definition where you fix some of the values to be at some particular base points. But I'll leave that out of these lectures. If there are m root nodes, then we get a m-fold tensor, and I'm going to call that a scaffold of order m. In particular, I know that J, the all-ones matrix, is the sum of the adjacency matrices. So it's really nice that I can take any two nodes, whether they're joined or not, and I can throw in J. That doesn't affect the definition on the previous slide, because if one edge weight is all-ones matrix, it doesn't affect this product at all. So I can throw in a J, and then I can expand and write that tensor as a linear combination as just a sum of tensors where I have every possible adjacency matrix on that edge. Okay, and maybe any of those will vanish for me. Likewise, I can always pull nodes apart, whether this was a hollow node or a red node, I can pull it apart as long as the new node I create is hollow. Put an identity matrix on there, and the identity matrix is the sum of the E's. And so each of these scaffolds can be written as a sum of scaffolds where the edge weight is a single primitive idempotent, and hopefully I do that in a creative way so that a lot of those things vanish. Okay, so deletion and contraction, in particular, well, I'll use this in just a moment. Okay, so some technicalities that yes, Maria. I already directed yesterday, I just didn't use them very much, but yeah, it's the same definition, yes, same definition, thank you. So, so we have to specify, and in our product, we take this standard basis vector for each element of X, call it X hat, and we set up in a product so that X hat dot Y hat is 0 if X is not equal to Y, and 1 if X is equal to Y. Once you have that, then you can identify the vector space with this dual space, and that allows us to identify matrices with scaffolds. My students and I actually tried one summer. We spent a couple of weeks saying, okay, what if you have some nodes for the dual space and some nodes for the vector space, so that matrices are in V dual tensor V, and really got very cumbersome, and we weren't able to simplify much. So this I think really is the right move. So that way elements in V tensor V are considered as matrices. Identify just the picture, the data displayed, we have the convention that is the tensor, okay? Doesn't represent the tensor, that is equal to the tensor, okay? So I'm going to put equal signs between these depiction of the data, okay? I mentioned before that these local moves are valid, that you have an identity that holds for scaffolds, and those scaffolds are embedded inside bigger scaffolds in such a way that the only things that interact with the rest of the diagram are red, then those changes are legal. Okay, so you can check. The edge weights are symmetric matrices. That's like what we were dealing with the proofs yesterday. The edge weights are symmetric matrices. We don't need to worry about the direction on edges because directing edges transpose the matrices. So we didn't need that really at all yesterday. Hollow nodes of degree 1, if the matrix has constant row or column sum, nodes of degree 1 just turn into scalars, and so they can be thrown away. Likewise, loops can be thrown away if they have constant diagonal, they just become scalars. So nodes of degree 1 and loops, they kind of vanish. So I introduced yesterday this idea of fixing the diagram. So you fix that little diagram, and then you think of the vector space spanned by all possible scaffolds where the edge weights come from this algebra that you choose. You look at all the possible tensors you can get as linear combinations of scaffolds with that particular diagram. And I think this is something really worth studying some more. And my questions at the end will probably address this. So we said yesterday, for example, if the diagram is a graph K2 with both nodes roots, then the vector space of all scaffolds is, if I identify this with a matrix, once I put an edge weight on there, that's exactly the algebra, the coherent algebra that I started with. And then we saw earlier that if you have a two-terminal series parallel graph, that is, you have these two root nodes, and it can be series parallel reduced to just an edge, then those things are also just the algebra that you started with, because our algebra, our coherent algebra, is closed under Entrywise multiplication and matrix multiplication. So all those edge weights can be converted to edge weights still inside the same algebra. As soon as you get a graph that's not series parallel, you start to distinguish things. So for the Hamming scheme, this is exactly Bose-Mesner algebra. But for the dual graphs that are not Hamming schemes, this is a larger vector space. This matrix algebra, this algebra of matrices is larger. So I should say this vector space of matrices. I haven't assumed it's closed under multiplication. So this vector space spanned by these scaffolds is larger for the Doob graphs, because the Hamming components and Doob components are differentiated. So I'm interested, what if I fix the number of roots? Say, okay, I want just 2 red dots. Okay, and now what possible things can I get if I have arbitrary number of hollow dots in there and I just have 2 red dots? How much bigger than the Bose-Mesner algebra can it get? 3 red dots. So these are these nth order scaffolds with edge weights in this coherent algebra. So I'm interested in fixing them and letting the number of nodes in the scaffold grow. For example, if I have m root nodes and just m nodes in total, that's a particular vector space. If I allow another root node, because I have the deletion and contraction, because I can use the identity in all-ones matrix to pull nodes and edges away, I know that this contains these. Every one of these can be represented by one of these. And that goes up, and then when I finally get to the number of vertices, now I know I have the entire thing. I'll outline that proof for you in just a minute. What point do you reach the full space of scaffolds with m root nodes? It's an interesting thing. It'd be really nice if there was some general statement you could make about, some sort of constrained class of association schemes to say that I reach the total number, I reach the full vector space when I get to half cardinality of x. It'd be really nice if it was independent of the cardinality of x. That would be an amazing statement, but it's probably not independent of the cardinality of x. You'll see at the end of this talk that it might be more interesting to just restrict to the vector space you can obtain by taking circular planar diagrams, right? Now just allow the diagram, so if you have m root nodes here, you can have the complete graph Km, right? But for here, if they're m bigger than 4, there are going to be diagrams that you can't build. Actually, even K4, no, K4 is okay. Yeah, in a circular planar graph. Okay, so I'm interested in this, and I'll end with something that really surprised me. That deals with these circular diagrams. So if I have all the edge weights in the coherent algebra, so our definition of the automorphism group of the coherent algebra, Crystal gave this already, and she called it a cellular algebra. The set of all permutation, the group of all permutation matrices that commute with every element of the algebra. So the dimension of the vector space of all scaffolds with m roots is exactly the number of orbits of the automorphism group on m tuples, on ordered m tuples of vertices. Okay, so that dimension is exactly the number of orbits, and you have a basis consisting of basis vectors of this form where you just sum these simple tensors over the orbit. How you prove that is you say, well, if I can take any number of nodes, let's just take the complete scaffold on cardinality of x nodes. Let's suppose my coherent algebra has n rows and columns. Just take the complete graph on n elements, and then just between any two, just write down the relation that joins those two, and you got this giant scaffold, and you have to. This has to be preserved by the automorphism group. So this gives you the dimension. So you'd be interested in cases where this is small dimensional. So distance transitive graphs should give you smaller dimensional third order tensors than distance regular graphs, and so on. And in particular, for distance transitive graphs, the second order scaffolds, I guess that vector space has dimension d+1. So in the theory of circular planar graphs, there's this concept of a rooted minor. So we had those roots on the boundary, and we do deletion and contraction, except that we can't collapse roots. The roots have to remain distinct. Okay, so there's this idea of a rooted minor. So we say that G contains a rooted minor with respect to H and root set R, if we can contract and delete the edges of G with R prime, where R prime maps bijectively to R. And if you have that rooted minor, then those all ones matrices and identity matrices allow you to see that the space of scaffolds with diagram HR is contained in the diagrams with GR, right? You're just taking all of those edges that you contracted, put identity on those, all the edges you deleted, put the J on those, and you get a diagram that that belongs in the smaller algebra. A lot of us are interested in this triply regular condition. We say that association scheme is triply regular if once I know the relations joining three vertices X, Y, and Z, and I specify other relations R, S, and T, then the number of vertices that are R related to X, S related to Y, and T related to Z is a constant. It only depends on R, S, T, and I, J, and K. And so that's exactly saying that these two vector spaces are equal. And so you take the circular planar dual of these, I wrote this down yesterday, I thought of this as the dual, take the circular planar dual of those two diagrams, and we call this really regular if those two spaces are equal. Now this space clearly contains this space because I can contract these three spokes that I can, this space clearly contains that space. I can contract the three spokes and get that. Clearly contains this space because I can contract the three edges of the triangle and get that. This space right here contains this one because I can delete the three edges of the triangle and get here. And it contains this one because I can delete the three edges of the spoke, and there's an isolated node which becomes a constant. And I get there. So these both contain that, but this I think is interesting. And I think I put this post-it up yesterday that Williams paper, we started with this, and then you applied these node actions and edge actions. The node action maps you into here, and the edge action maps you into here. But then you can go up and you sort of get outside the Terwilliger algebra. It seems, we're not sure, but in a generic sense, in a generic case, you're going to get outside the Terwilliger algebra after a while. So, so this containment, if you have a coherent algebra, this containment, it's interesting when this poset collapses, when things terminate. So I'm going to define the T algebra in this strange way to be the vector space of all linear combinations of scaffolds of this form. So this is an element M star M, M star M, M star M, etc., and M star. And you have a certain number of nodes on the bottom, L plus 1 nodes or L edges on the bottom. And let's just take the sum of those vector spaces. And it'd be really nice to see this sort of terminate at some point, right? Have some control in the association scheme and say, okay, at some point, these things terminate, that there's some kind of Esky-Wilson or Q-cell relations that allow you to push elements around back and forth, right, and collapse things. If you fix this base point right here to be a single node, then this looks more like the matrix algebra. And I think that Paul realized that we have a lot more matrix theory available to us than we do have theory of algebras of third-order tensors, and there's a lot you can do just by fixing a base point. This node action and edge action show up in both the Terwilliger paper and in Francois Jager's paper. And so in the node action, we multiply a particular tensor component by a matrix M, and that does this to the diagram. Okay, there should be a directed arrow down if it's a non-symmetric matrix. In the edge action, we choose two of these roots, and we just attach a matrix M to the side. Okay, now you can do this anywhere, any number of root nodes. You can put a node here, you can do a node action here, you can put an edge here and here. All of those things are available to you. And this really interesting question, starting with the triangle, starting with the tensor, the scaffolds you can get from a simple triangle, what's the smallest space that you can build that's stable, that doesn't grow anymore when you apply these actions on all possible vertices and edges? And 3 choose 2 equal to 3 makes 3 kind of a very special number that there's some kind of symmetry between nodes and edges only for. Now, the node action, the edge action is Jaeger's terminology. In Terwilliger's paper, this is the edge action right here, is this projection. So you take a tensor of this form, and you only retain the triples, right, the basis tensors, where x and y are joined by relation I. So that's exactly putting AI between x and y, put AI, and that throws away all of the tensors except for those where that node and that node are I related. So that's the edge action. And then the node action, you project, so Terwilliger in 1987 just uses E's because they span the Bose-Mesner algebra. You take EI and apply it just to that component Z, and that's this right here. This is EI applied to that component Z in V tensor V tensor V. Okay, so you're working in V tensor V tensor V, and you have these actions, and so you see this in 1987, and then in 1992, my viewpoint, and since the author's in the room, I shouldn't say anything. My viewpoint is that Terwilliger thought, okay, but let's just move one node alone, the one at the top, and then apply node action on the two bottom ones, so you can go out this way, and edge action between the top one and the bottom ones, and that's where you get, that's where you get this, right? So node action allows you to grow this path at the bottom, and the edge action allows you to add matrices on. You can do that on either side, but in the T algebra, you're leaving one of those three alone. Okay, just to get a control on things. So when does this terminate? Well, this is a nice theorem that if it's triply regular, then everything terminates at T. Because through the triply regular, you get this is equal to that full T. Okay, so things stabilize very quickly in triply regular and dual triply regular case. Let me prove something a little bit different. Actually, when I checked my slides this morning, I found that I had this theorem and the proof of something else following it, so I had to stick in the thing that I actually did prove. That's right. Something that I didn't state. Yes. So suppose this, I call this tri-star, I don't know why, but suppose this vector space is contained in this vector space. Now, I've already mentioned that obviously this vector space is contained in this one because I can contract, I can take anything in here, let's say I have edge weights L, M, N, I can put L, M, N here and identities on those three spokes, and I have the same exact tensor, right? So I know that this is contained in the one on the left, but if that's contained in the one on the right, then the Terwilliger algebra in this third order tensor form is just nothing more than M star M, M star, right? Direct sum over all vertices. Okay, so here's the proof. So assume that that's contained in this. Now, let's just go by induction, add on just one more triangle in the bottom. If I can remove one triangle, then I can do that inductively for any number of triangles. So now let's split this node at the top and put an identity matrix. And you can split a node in any way. When you split a node, the edges that run to that node, you can distribute them however you like. And so the two edges that are weighted B and C, I'm going to direct those to the new node. And the edge A, I'm going to go send over there. And then I'm going to multiply this by the identity, get this. And now you look at that, that's exactly this tri-star. We're assuming that that vector space is contained in the space of triangles. So therefore, that tensor is a sum of tensors of this one. I was going to say linear combination, but you can always observe the scalars. So now you've got the assumption that that gadget is a linear combination of these gadgets. So I can take that gadget right there. So I'm just repeating what I had, assuming that that gadget is the sum of these gadgets. I just repeat that. I can replace that gadget on the left diagram, replace that by this sum here, and it's a sum of scaffolds that look like this. Our algebra is a coherent algebra, so we're assuming that it's closed under Entrywise product. So that is in this space. Okay. And this isn't really probably a new proof at all, but new theorem at all. But the proof is so easy using graph theory that it almost looks like it's unfair, right? You're proving that these algebras, that these vector spaces are contained in one another. Any questions about that? So back to these circular planar graphs. What would happen if?
So what did you just? You put the algebras that contain each other.
Then anything with an arbitrary number of nodes at the bottom, right? Any one of these can be reduced to a single triangle, right? Inductively using that step to leave the induction. So I just got rid of one triangle, right? I just took one triangle and I got rid of it. And then if you had 10 triangles, this argument gets rid of the 10th one, and now you're down to 9 triangles, and you let somebody else do the other 9. You end up with something that's just in this apparently much smaller vector space, but it turns out that they're equal. Good question. Anything else?
So did you resolve the issue of if you're triply regular, does it have to be formally triply regular?
Really? No, I didn't. I didn't prove that triply regular is equal to. I did not prove that these are equal. Yeah. So if it's triply regular, then this is equal to this, then this is equal to that. So yeah. So I didn't include that in the slide. Yeah. So then triply regular, if and only if duly triply regular. I think that's in the notes, and I just slipped my mind.
Because I feel like we discussed this yesterday in the non-knowledge, like the open question type of.
Right. And
this slide
say that they're the same thing.
Yeah.
I'm just trying to think if I have an extra assumption in there. No, I think it allows you to get this, but let me talk to you afterwards and make sure that. Yeah.
Maybe okay.
Yeah.
It's in the term you swap the locations of all of the stars. Then the module generated by AI star. They should also be small. So I think it should also be dually, triply regular. However, did you assume the diagrams at least 3?
No, I don't have an assumption the diagrams at least 3. Well, I did give you the proof of this, so let me come back to the paper and check if there's an assumption in there. Thanks. We'll discuss that afterwards. So back to the graph theory. If you look at circular planar graphs, right? As long as the edge weights, so we're going to work inside of Bose-Mesner algebra so that our matrices all have constant diagonal. If they all have constant diagonal, it's just become scale. Loops with edge weights in the Bose-Mesner algebra become scalars. Nodes of degree 1, those are just multiplied by row sums, and if all the row sums are constant, those are just scalars. So we can remove loops, we can remove nodes of degree 1. Parallel edges can be replaced with single edges by Entrywise multiplication. Edges in series can be replaced by matrix multiplication, by single edges with matrix multiplication. If I have this equality, then every triangle can be replaced by, if I have a scaffold with a triangle, I can replace that by a sum of scaffolds, where that triangle in each of the scaffolds is replaced by a star. And likewise, every star can be replaced by a triangle. So I just blew that up. That was written in very small text. So here it is again. But I'm really interested in the assumption that was at the top of that previous slide. If those two vector spaces were equal, then every single two-terminal planar graph, a circular planar graph, is reducible to a single edge by these operations. Okay, I don't know how to remove the black box. Yeah, that's on that computer. So yeah, this is exactly this sentence. It's exactly this sentence. Exactly this sentence is repeated on the next slide. Okay, so there's nothing else. So these are exactly the operations you need to reduce a two-terminal series parallel graph to a single edge, okay, to a single edge. And we know that the vector space of second-order scaffolds with a single edge is the Bose-Mesner algebra. If you have that those two spaces are equal, then every planar scaffold with 2 root nodes is in the Bose-Mesner algebra. So it doesn't matter how many right nodes there are, as long as the graph is planar. And remember, those are counting homomorphisms from that thing into your association scheme, right? So you're looking at embeddings, you're counting embeddings. Given 2 root nodes, you want to know how many embeddings of this planar graph into your association scheme have these 2 root nodes. It only depends on the relation between those 2 root nodes. But it's only for planar graphs. Remember, we talked about this strange duality between this duality of circular planar graphs and the duality of association schemes collide now and then. And this really, really amazed me. So we saw this slide earlier. We take the circular planar dual of this diagram, and then we just replace the weights. All the edges get rotated 90 degrees counterclockwise, and the weights are the same, and that swaps entrywise and matrix multiplication. I think that we as mathematicians, we have to be optimists. We have to believe that structure exists. We can't be hopeless. So we have to hope for things. So I made this conjecture, which was wrong. So basically, I wanted to say any theorem about Bose-Mesner algebras whose hypotheses and conclusions can be all expressed as scaffold equations has a dual theorem. Okay, that's number one vague, number two wrong, number three imprecise. But what's that? Yes. So any theorem that you can get, you replace the diagram by its circular planar dual. So if you have expressible scaffold equations with circular planar diagrams, I left out that hypothesis. Even here, it's imprecise. You can replace it by the circular planar dual, replace the AIs by EIs, and vice versa. Replace PIJKs by QIJKs if there are scalars, then you should have a dual. It's this beautiful paper that just came out by Xiaoye Liang and Tan and Hajime Tanaka and Wang. I forgot first name, Xingxin Wang. I forget the first name. If you restrict to translation association schemes, that conjecture, when repaired, is true. A translation association scheme is one where you have an abelian group acting transitively on the vertices. Well, you take a subgroup that acts regularly on the vertices, you can identify the vertex set, the elements of that abelian group, and you want to assume that the translation by any element of the abelian group is an automorphism. Okay, so this happens with the Hamming scheme, with things that are defined in terms of cyclic groups and so on. So there are a number of important, the bilinear form scheme, the Hamming scheme are the main examples, and coset graphs of completely regular codes are examples. We have a translation association scheme. Okay? So in that case, there's a way in Delsart's thesis to construct a dual association scheme. There's something more general in Delsart's thesis, but I just need the one that's built from the characters, linear characters of an element of an abelian, finite abelian group. And you get a dual Bose-Mesner algebra A dagger. This is not the dual Bose-Mesner algebra of which Williger theory talks of last week. You get a dual adjacency matrix, you get a dual idempotent. So a fundamental example is K33 and the octahedron. So these are both translation schemes for the cyclic group of order 6. And K33, the valencies are 1, 3, and 2, and the eigenspace dimensions are 1, 4, 1. For the octahedron, the valencies are 1, 4, and 1, and the eigenspace dimensions are 1, 3, and 2. So that's sort of the example that I always give to students of a dual pair of translation association schemes. There's a natural bijection. The AIs correspond to eigenspaces of the duals, and the relations of the dual correspond to eigenspaces of the original association scheme. So this is a translation association scheme. Well-known topic, but might be something that you haven't seen before. So just this year, Liang, Tan, Tanaka, and Wang proved that if you have a translation association scheme, then for m at least 1, there's a special case m equals 0 that I didn't have room for on the slide. There's an isometry from the vector space spanned by all planar mth order scaffold with edge weights in that Bose-Mesner algebra to the vector space spanned by all mth order scaffolds with planar scaffolds, circular planar scaffolds with edge weights in the Bose-Mesner algebra of the dual scheme. The way this works is you take scaffolds whose edge weights are just among the AIs, right? Just among the AIs, and you replace them, the dual, when you rotate an edge by 90 degrees, you replace the weight by the corresponding EI projection onto the eigenspace of the dual association scheme. And I completely missed this scalar. in my conjecture. There's a scalar up front, certain times the number of vertices. I was really thinking of putting all equations equal to 0, and I didn't realize that different components in the equation have to be multiplied by different scalars. And also you need to make sure that there's sort of a unique embedding of the circular planar graph. Otherwise, if you get two different embeddings of the graph, you might not get the same rule. And so assume that the graph is weakly connected, that is the underlying undirected graph is a connected graph. And there's some other things that the nodes have to be put in a consistent, what they call standard order. So standard weakly connected planar scaffolds. So this isometry tells you that if you have statements that are expressible in terms of orthogonality and so on between different scaffolds, then that dual theorem also holds true. And this was an excitement for me to see that paper on the archive when that came out. So I think I'm almost out of time. Let me just finish with what I think are some interesting open questions. So we started the week talking about cometric association schemes, and we have primitive schemes that are not P-polynomial with d equal 3. I think there are a couple sporadic things with d equal 4. Do there exist any primitive cometric schemes with d equal 5 or 6 that are not metric? I don't think I know. Well, there might be one on my table, but are there more than one? We talked about these Q-antipodal, Q-bipartite 4-class schemes. We know that the dimension has to be 0 mod 4, just as in Akihiro's talk this morning, because you have to have a Hadamard matrix in order to build these things. And there's many dimensions where we don't know the maximum number of real MUBs. It's sort of similar to finding the maximum number of orthogonal Latin squares. I'm not going to say the problems are equivalent, but mutually orthogonal Latin squares can give you MUBs. This is a result of Brian Kodalin, but it's not clear what the upper bound is. Likewise, it's not clear what the upper bound is on linked systems of symmetric designs. So linked systems of symmetric designs, we have these nice papers of Jedab and Lee and Simon, and myself with Jim Davis and John Polhill, that construct these things via linked systems of different sets, linking systems of different sets. And I think this has not been studied very much at all. Finding different sets, you have an equation in the group algebra, a system of equations in the group algebra that you have to solve, and people who understand different sets, I think will attack some of these at some point. Just generically, this bounds on the number of fibers in a Q-antipodal association scheme. When D is odd, we can prove that this number is bounded by M1, but in the even case, we can only prove that it's bounded by the second multiplicity, which can be as much as like M1 choose 2. So that is a gap that needs to be fixed. So we need to find an upper bound, a uniform upper bound on the number of fibers in the Q-antipodal scheme. When D is large, we'd like to say a primitive scheme must be primitive cometric scheme must be metric. If it's not metric, then it's probably imprimitive if that conjecture is correct. But it seems that the Q-antipodal schemes, when you get to a large number of fibers, when you get to a large number of classes, the number of fibers just becomes 2. Remember, P and Q polynomial, Q-antipodal becomes P bipartite, and in bipartite ordinary common language, there are only 2 colors, right? But the generalization to Q-antipodal allows for more fibers, but I got a feeling that when D gets large, there should only be 2 fibers. That should be the case. We still haven't resolved the unimodality conjecture that with respect to a Q polynomial ordering, multiplicity should be unimodal. I think we can do this by interpreting the eigenspaces as spaces of polynomials modulo some ideal, but I don't have a proof. We'd like to say that as you get a Q polynomial scheme with a large class number, that the thing looks like a P polynomial scheme. So maybe instead of saying that Pijk is 0 whenever k is bigger than I plus j, maybe there's some threshold, maybe 5. If k is bigger than I plus j plus 5, maybe things go away. Because you're betting things on a unit sphere, And if the smallest angle in that spherical code gets small, the two things that are just close together in that distance, in that nearest neighbor graph, they can't be joined to things that are far away. So things should spread out uniformly across the sphere. And so you'd like to say that there's some constant L such that this intersection number vanishes when you look at that ordering, the natural ordering coming from the decreasing cosines in that first eigenspace. Questions now think about the scaffolds. Can we do any better than the number of vertices? We know that the space of mth order scaffolds with edge weights inside a coherent algebra A, we know that that vector space is reached when you get to number of nodes equal to the number of vertices. Can we do it better than that number of vertices over 2? Or it'd be wonderful if for some class of schemes you could have a bound on that number of nodes that's independent of the number of cardinality of X. For example, in particular, for which association schemes are the 4-node scaffolds giving you everything that's a third order scaffold with weights in that Bose-Mesner algebra. Paul Théorie challenged me, and I lazily passed the challenge on to you. I'd like to get to it, I hope. Work out the vector space of scaffolds, mth order scaffolds for the complete graphs. What if you just have the Bose-Mesner algebra, the complete graph? All your edge weights can just be taken to be I or J, and let M grow, and let the number of nodes be arbitrary. It should be possible to describe these spaces of tensors. Okay. And then Paul and I, both for a while, but Paul challenged me even this week, to find things other than the stars. Right? We know that if Qijk is 0, then this little star scaffold has to vanish. And if Pijk is 0, this triangle scaffold has to vanish. But maybe there are other scaffolds, there are other configurations, such as there are other graphs that cannot be an induced subgraph of any distance regular graph. Are there things like this, or an induced configuration? You're more than just induced subgraph because you can specify distances, right? But is there anything that's violated that isn't just violated by the triangle inequality? Is there anything that's forbidden other than the triangle inequality? That would give you a scaffold that must be 0 for all Bose-Mesner algebras. Independent of all this, I haven't spoken to you about these nice papers of Penjic and Neumeier on distance regular graphs, where their scaffolds are 0th order scaffolds, and they sort of are taking averages. So there's a scalar out front, and they have techniques that are very powerful for saying things about the intersection arrays of distance regular graphs. And it could be that the two approaches can reinforce one another. So we might be able to learn something from their techniques. For example, we might be able to dualize some of their theorems about distance regular graphs and get some statements about cometric association schemes. I apply these things very, very concretely because my co-author Jason Williford has generated a large number of open parameter sets, and we can't rule these things out using the techniques we know. So I'd like to build a way to get scaffolds that say, if this extra Klein parameter vanishes beyond the obvious ones that come from the triangle inequality, if this extra Klein parameter vanishes, then some other Klein parameter should vanish by something like Dickey's prism or one of those proof techniques that maps information far out in a distant eigenspace back to the first eigenspace. So that's one of the things I'm interested in. So thanks very much for your time. You folks really been kind to me this week. Thank you.
Do you have any questions for Bill?
Still has questions.
You go.
Oh, okay. So suppose I have some class of scaffolds such that under series parallel reduction and delta Y transform, it eventually goes to a single edge. What does that mean for the class it started with?
But you haven't specified the edge weights.
Over some cellular algebra.
In a particular cellular algebra, you have a class of scaffolds where everything you can get is in the cellular algebra. So that tells you that if you have those edge weights, that tells you that every homomorphism from one of those underlying diagrams into every mapping from one of those diagrams into your coherent configuration, where you can specify between on any of those edges, you can make a restriction as to what relation you want to happen between those nodes. That number of homomorphisms only depends on the relation between the two roots, or the pairwise relation, or the pairwise relation between three roots. Well, for any kind of that again tells you the same thing. Anything that you can get that reduces to a single edge that tells you that the number of homomorphisms from that object with, again, we're not just assuming that the object is a graph, we're assuming that every edge has a specified relation. The number of such maps into your coherent configuration only depends on the relation that joins the you've chosen.
So graph theoretically, the forbidden minors for reusability via delta y and clusters parallel is not fully known. But for example, we know some forbidden minors, like the Peterson family, who are trying to be
And K6, yeah.
yeah, so
Yeah.
meaning that
Forbidden.
if I have a scaffold, this underlying graph is Peterson graph, then
Means it's non-planar. it's,
that's my second.
No, I mean, the planarity is a crutch, right? So when you have planarity, you've got this sort of these reduction tools, but you've also got some seeming connection to association scheme duality, but you have the definition of a scaffold doesn't depend on planarity at all, and these statements about those being equal to the full space of tensors aren't related, don't depend on planarity or anything like that.
So you have made this choice for the circular planar graphs that you drew. So it will be on like a boundary surface, and then you have an embedding on the door. So what would happen if instead of taking it on a little disk, it's like on a little mini crossgap, it would give some other dual.
Right.
Have you considered what that other dual relation means, or what it looks like in the scheme?
So if I took this, I would guess that this correspondence would fail, right? So this correspondence between dual graph and dual and Bose-Mesner algebra, I would guess that would fail. Maybe a cross-cap dual gives you, well, I would be suspicious because a cross-cap dual could be locally planar, and you're sort of going to be forced to have this at least on that part of the diagram. It's only the stuff that goes through the cross-cap that's going to have to obey your new algebraic rule. So I think it's worth a try, but I think that doesn't sound like you're going to get something elegant. Yes, Paul. Microphone.
Here's a question I wondered about.
It happens to be all the time. Glasses hooked on mask. Yes.
Okay, so the problem is this: you've consider a scaffold with 4 red nodes. Let's see, we're going to be summing over all 4 nodes. And we specify the 6 distances. AI, so we attach an edge weight AI, AJ, AK, AR, AS, AT, and then we sum over everything. And so we're effectively counting the number of 4 vertex configurations in our graph with those 6 distances.
I'm listening.
Right. Okay. Now you automatically get a non-negative integer because we're
They're all root nodes. Is that what you
so
said?
no fixed nodes. So we're summing over everything.
They're all hollow. Okay.
They're all hollow.
Okay.
Okay. Now dualizing this, we replace every distance matrix by a primitive idempotent. So on the edges now we look at EI, EJ, EK, etc. Yeah, and we leave everything. We leave everything hollow. And now the question is the result, which is going to be some scalar, is that still still non-negative? Is that still non-negative?
So I think I have a counterexample in yesterday's talk. From the Peterson graph, I have a K4. It's in the Peterson graph, just in the small example, Peterson graph, I have this equal to -2/243 or something like that.
Oh, is that right?
Yeah. So for the Peterson graph, I have a counterexample where that is negative, just E1s and E2s.
Oh, all right. Oh, that's very interesting. Okay.
Okay, do we have more questions? Well, if not, then let me thank you, Bill, for the amazing work this week. It was very nice.
Thank you.
And we all learned a lot. Thank you very much.